Hello and welcome to another video. In today's video we're going to be going over topic 3.7, the application of the derivative in the sciences. So before we begin looking at all these applications of the derivative, I think it's important for us to know what the derivative represents. We know the derivative represents a instantaneous rate of change of a function. However, math is not the only thing where rates of change occur. In fact, in this section, we will see some of the many applications of the derivative. In fact, you'll see applications in the derivative like in all sorts of fields like physics, chemistry, business, and so much more. So what we're going to do in this video is go over some of these real-world applications of the derivative. So it's just not math on a page, but it's more like you get to see what it's used for. Well, if we want to know how a function changed for some certain values, we know that we can find a change in y, and it's corresponding to a y2 minus a y1. Okay. Well, if we want to know how long it took for that change to occur, we can take the value of x that's tied to that y and say that x2 minus x1. If we want to know the average rate of change, we just divide them. Okay. If we want to know the instantaneous rate of change, we take the limit as x2 approaches x1. And of the change of y over change in x. And that gives us dy dx. But all of these things have in common is it's an average rate of change. And why is this important? We're going to be seeing this average rate of change in several of the following fields. Before we get started on this velocity problem, I should have probably given myself a bit more space. Let's ask ourselves, what is velocity? Well, the way that we might find average velocity, well, velocity is defined as the change in position over a change in time. Okay. Well, velocity then in that case is the same thing as x2 minus x1 over t2 minus t1. What does this look like? This looks like an average rate of change, and you would be right. If we want our instantaneous velocity, all we have to do is say the limit as t2 approaches t1 of the change in x over change in t. That is equal to the derivative with respect, or the derivative of a position with respect to time. And that's the definition of velocity right there, instantaneous velocity. So what you'll see is that this concept of this derivative, we're going to be seeing in all sorts of fields, including physics, for the first one that we're starting out with. So for this, I have a little practice problem for us, and it says a particle's position is given by s of t is equal to 1/3 t cubed minus 7/2 t squared plus 12. Okay. And t is in seconds, so find its velocity at time is equal to t. Find its velocity at 1 second and 5 seconds. When is the particle at rest, and when is the particle moving forward? Okay, so to get started, we know that s of t is really just the position of the particle. So if we take the derivative of that, so we have s of t, and we're going to take the derivative with respect to t, is equal to the derivative with respect to t of 1/3 t cubed minus 7/2 t squared plus 12. I believe that's supposed to be a t. And after this, I'll change my color just to make my stuff stand out. Show favorite spot, and we'll say that you're going to actually be on top for once. Okay. Well, this is going to be the velocity of t. The derivative of t, 1/3 of t cubed is t squared. The derivative of t, 7/2 of t squared is 7t. Plus 12, the derivative of 12t, which is just 12. And that's our answer for A. All right. We're going to have to once again clear the board. So now it wants us to find our position or velocities at 1 and 5 seconds. So we just take the velocity of 1 is equal to 1 squared minus 7 times by 1 plus 12. 1 minus 7, that's negative 6, plus 12, that's a positive 6. And our v of 5 squared is 25 minus 35. That right there is a negative 10 plus 12. That gives us 2. Okay. How are we going to find when the particle is at rest? Well, what does it mean for the particle to be at rest? Well, the particle is going to be at rest when v of t is equal to 0. So we're going to set this original function to 0. So what we're going to get is 0 is equal to t squared minus 7t plus 12. Now what we can do is we can either use the quadratic form or factor it. Let's try and factor it since that normally works out cleaner. We need a number to multiply to negative 7, but adds to, multiplies to 12, or adds to negative 7. And I believe the numbers that are going to do that is negative 3 and negative 4. So 0 is equal to x minus 3, or x minus 4. So now we just have to solve these for 0. X minus 3 is equal to 0. We need to add 3 to both sides. So we get x is equal to 3. X minus 4 is equal to 0. So we need to add 4 to both sides. So we get x is equal to 4. All right. So that makes our answers for this problem. X is I should rather say t is equal to 3 and t is equal to 4. All right. When is the particle moving forward? Okay. Wonderful question. Well, we would normally define forward as positive. So we want to know whenever this function's positive. So a neat little trick that you can do is we'll draw a number line. And we'll put our 2 zeros on it. So we know that this function has zeros at 3 and 4. And then we're going to plug in values that are either much bigger than 3 or 4, or much smaller than, or in between. Well, we know that this factors out to be x minus 3, t minus 3, and then t minus 4. And that's going to be the ideal form for this. So if we're way out here at negative infinity, this is going to be negative, and this is going to be negative. A negative times a negative is a positive. So, let's see. Then, for times from 3 to 4, well, we know that this over here, the t minus 3, that's going to be positive. But this t minus 4, if we plug in a 3.5, that's still going to be negative. So that's still negative. Finally, for this last one, we know that we're plugging in very big numbers. Let's say we plug in 1,000. Well, this first term, 1,000 minus 3, that's still pretty close to 1,000. That's still very positive. 1,000 minus 4, that's also still very positive. So we get that from negative infinity to 3, it's moving forward. From 3 to 4, or it would be moving backward. And then from 4 to infinity, it would be moving forward. So what that would look like, using interval notation, is it will look like negative infinity to 3, including, and then 4 to infinity, excluding. Close bracket means including, open bracket means that it's excluding. Alright. For this next problem, or for this next topic, or rather for an introduction of this topic, chemists will oftentimes have to measure the rate at which, or not really the rate, but the amount of chemicals at a certain time is reacting. So they will do this by measuring the amount of or molecules produced by a reaction. So in this example, I've given us a reaction where there's going to eventually, well, it's going to produce a certain amount of particles. And our goal is to find how many particles it's producing and how's that changing with respect to time. So the amount of water produced from the reaction H2 plus O creates H2O is given by H2O of T is equal to the natural log of 5T with T in minutes. Well, I don't know if this is actually true or not. I'm pretty sure I'm just BSing it. But it's still here for us to do some calculus practice. So we want to find a change in H2O molecule from 5 minutes to 10 minutes. So notice that this is just a change in like the H2O. Or we can even call this Y. Well, what we need to do is we need to just plug in time is equal to 10 and time is equal to 5 and find the change in that. So, change in H2O is going to be equal to H2O of 10 minus H2O of 5. We know that H2O of 10 is equal to the natural logarithm of 5 times by 10, which is 50, minus the natural logarithm of 5 times by 5, which is 25. Using our properties of logarithms, we can simplify this to be the natural log of 50 divided by 25, or just the natural logarithm of 2. And that is our answer for the first question. That's a good spot for it, ish. Okay, for this next question, we want to find the change in H2O divided by the time. So we already have the change in the H2O. I guess I should have specified at T is equal to 10, T is equal to 5. So we take this natural log of 2 and put it over 10 minus 5, which is going to give us a result of the natural log of 2 over 5. Or if you want to rewrite that, that's also the same thing as natural log of 2 to the power of 1/5. Not very much more useful like that. Now we want to take the derivative with respect to time at time t of this change in H2O. So what we're going to do is we know that H2O of T is equal to the natural log of 5T. we're going to take the derivative of this with respect to t, and we're going to get dH2O over dt is equal to, using the chain rule here, we know that the natural logarithm of 5t, taking its derivative with respect to 5t, is 1 over 5t, times by the derivative of 5t, which is 5. This 5 and this 5 will cancel, leaving an answer of just 1 over t. Okay, now what do we do? Well, that's it. This is our answer. Now all we have to do is find the derivative of H2O with respect, or evaluate the derivative of H2O with respect to t at time is equal to 5. So our dH2O dt evaluated at t is equal to 5 is just equal to 1/5. And that's our answer. So now we have biology. How is the derivative related to the science that deals with population and how cells work? That is a wonderful question, you may ask. Well, you may know this from biology, but oftentimes our bodies are reproducing. Whereas, in general, this rate of reproduction is most certainly not continuous. In fact, it will look more like a staircase rather than a continuous function. We can still model these changes using functions, continuous functions. So what we do, or what biologists might do, is, let's say that they want a population. Oftentimes biologists want to know how a population is changing. Change in population is just population 2 minus population 1. Okay. Now you might want to know, how's this population changing with respect to time? So this change in P is equal to over change in T is equal to P2 minus the population 1 all over T2 minus T1. Why might a biologist want to know this information? Well, if a population suddenly takes a dive, let's say that for whatever reason it was growing, but now, because of some factor, it just suddenly drops. This will help a biologist know that this population is dropping, for one. And for two, it will allow them to take precautions to hopefully save this dying species. And you might have to do that a lot if you're working with something like endangered species. Or you might want to know, how's this population of this endangered species changing? For example, there's only 1,000 or less axolotls left in the wild. Very sad statistic, I know. I love axolotls. But our issue is that their population is seemingly still decreasing. So biologists might be tracking their change in population, the derivative of population with respect to time, to see if it's still decreasing or is it increasing. Because these factors are important for saving a species. So we're going to work at a real quick example here. A biologist is testing two separate strains of bacteria. He finds that strands A population is given by A is equal to 2.1 to the power of T and naught, and strain B's population is given by B is equal to 2T and naught. Assuming that n naught is equal to 2, find that the derivative of a with respect to t, the derivative of b with respect to t, at t is equal to 4. Okay. Well, to start out, let's start by taking the derivative with respect to a. So a is equal to 2.1 to the power of t times by 2, because we said that n naught is equal to 2. Now if we're taking the derivative of this, dA dt, we will get the derivative of an exponential, which is the natural log of said exponential, times by the exponential, times by 2, of a. And now we just have to plug in time is equal to 4. And we see after 4 seconds, or sorry, I believe this would be in hours, apologies. I just never stated that. Our dA dt evaluated at 4, t is equal to 4, is equal to 26.96, so we're just going to say 27 because we're dealing with population. Okay. Now how do we do this for dB? It's the exact same. So the derivative of b with respect to dt is going to be the derivative with respect to t of 2t times by 2. Which, in all honesty, we're just going to call this t plus 1. So dB dt is going to be equal to the derivative of the base, which is 2, or the natural log of 2, times by the derivative of the exponential, which is 2t plus 1, times by the derivative of the function that's inside the exponential, which is just 1, so we're not going to worry about that. Now let's evaluate this at 2, so we get dB dt is equal to the natural log of 2 times by 2 to the 4 plus 1, which is just 5. Plug that into our calculator, and we get 22 point nothing, because we're dealing with population. And you may notice I changed this value because I plugged it into my own calculator wrong. And I accidentally plugged in the natural log of 2 instead of 2.1. Anyway, from this we can see that at time is equal to 4, this function, dA dt, is definitely growing faster. So dA, or A, or bacteria A is growing faster. Being faster at time t at t is equal to 4, because dA dt is greater than dB dt. Okay, now what do we do? What do we do for this wonderful last question? Which one is more likely to take over the world? Of course, I wrote this question as a joke, but it does have an answer. The answer to the question is whichever one grows faster. And the reason for that is a very biological topic, but it's because it is more likely to grow strains of resilience over time. So we can very clearly see that the natural log of 2.1 is greater than the natural log of 2. What's it called? times that by an exponential, which is also greater than 2, and we will see that this dA dt is going to grow at a faster rate. So A is going to take over the world, or is more than likely to take over the world. Will it? Probably no. Alright, economics. Gotta love business. I'm a very businessy man. But let's see. So, we're going to start out with the cost function. What is the cost function? Well, it's basically saying cost of x, where x is equal to the number of things bought I probably spelled that. Yeah, I think that's how you spell bot. I might be wrong. I don't really care. There's a reason why I want to go into math, not English. So, what does the cost function tell, like, a big corporation? Well, it tells you how much is a certain number of items going to cost. Let's say I wanted to buy in bulk and say I want 3,000 let's see, 3,000 tires for cars. Tires. Okay. Well, if I plug this into the cost function for tires, and the business guy over there says, well, we have a certain price for, let's say, having 1,000 tires, or buying that many tires, and then let's say that it's also going to cost you $5 or $50 a tire. But for every tire you buy, it will get cheaper by like 0.01 cents or something like that. 0.01, or yeah, something like that. Well, the company can plug this value in to find how much is this going to cost. Okay. Now what are we going to do with this? Well, sometimes you also want to know how much is the change in cost going to be for a particular amount of items. If I want to know the change in cost over a change in like items, let's say I want to know how much is it going to cost me to buy 3,000 items compared to 2,000 items. Do I have the money to afford this 3,000? Do we want to know how much is that going to save us later on? Alright. And that's with respect to... And then what this gives us is this is going to give us the average cost per item. So what we can use this average cost for item for is, let's say, selling this at a price that's going to make us a profit. Now, another thing you can do with this is once we take this derivative, or once we take the limit as change in x approaches 0, we get something called marginal cost. And what this marginal cost does is it allows us to, let's say, tell you the price or how much price is going to increase if I buy, let's say that I'm going to buy 2,100 tires. Well, the marginal cost function will tell me, well, if I take dc over dx, evaluated at x is equal to that, this is going to tell me how much is it going to cost for me to get, let's say, another 2,000 or another tire. And that's going to, if I want to run that again at that 2001, that's going to tell me the price to get another tire. And then another. So this is really applying to the laws of bulk, because at a certain point, these rules for buying in bulk are going to allow us to make a bit better deals. Overall, all of the topics we've gone over today represent rates of change. And you'll see there is thousands of rates of change in the world around us. I hope you all have found this video informative, even though this video is more or less a review. I hope you all have a wonderful rest of your day, and enjoy. Goodbye.